I will prove the average translational energy of a gas phase species is half kBt in each of the three dimensions x, y, or z, assuming the Boltzmann distribution, which states the probability of a particle having energy epsilon is proportional to exponential function e to the power of negative epsilon divided by kBt. And first, we will assume that if we have a particle with a speed between Vx and Vx plus dVx, this dVx is infinitesimal, its exact differential of Vx is proportional to this exponential function, but over here I will replace epsilon with the kinetic energy, and it's also proportional to this interval dVx. And this is a proportional sign. We can replace this with the equal sign. If we insert a normalization factor here, and we can decide the value of A by integrating from 0 to infinity for the speed. The physical meaning is simple. The probability of finding a particle with a speed between 0 and infinity in the x direction is 100%. And we just need to evaluate this integral. And we set q squared equals half m Vx squared over kBt. And we can easily tell that this Gaussian function of Vx is transformed into e to the power of negative q squared. And also we know that Vx equals q. So over here we take the square root of both sides, multiply by 2 kBt over m. Using this, and again, if Vx is from 0 to infinity, q is also from 0 to infinity. And now it's pretty easy to solve if we know this value. This is the integral of a Gaussian function from 0 to infinity. The value is square root of pi over 2. We can prove this easily by converting an integral from Cartesian coordinates to polar coordinates in a two-dimensional area. But for now, I'm going to just use this number here, A, times square root of pi over 2 times square root of 2 kBt over m equals 1. Therefore, the probability of finding a particle with a speed between Vx and Vx plus dVx equals this A. We know this A now just by moving this two factors to the right hand side. It's going to be (2m) on top and pi kBt on the bottom. That's the normalization factor A multiplied by the exponential function here. Now we'll have to evaluate this, the average of half mv squared. How do we do that? It's very simple. We modify this integral. If you look at this integral inside, this is a probability. But we just need to multiply this probability by the kinetic energy. And we plug in this A here. This is your A, the normalization factor. And then we integrate whatever is inside. It looks complicated, but we can set, again, variable q squared. We'll do this again, and again we will replace this Gaussian function of Vx with e to the power of negative q squared. Half mv x squared is kbt times q squared. In dvx, again, we have the expression of vx, so dvx is simply 2 kbt over m and then dq. So we can do a lot of cancellation. kbt in the square root, kbt in the square root, m in the square root, and this m in the square root. And we have a square root of 2, square root of 2. So it's going to be 2 over square root of pi here. And then we have a kbt here. So we copy the kbt, and then we do the integral of e to the power of negative q squared. This value is square root of pi over 4. We can prove this again by converting Cartesian coordinates to polar coordinates, or simply use Mathematica or wolframalpha.com online. Anyway, the value of this integral is square root of pi over 4, and now we can cancel the square root of pi and the 2, 4. We have half kbt in the end, done.